So if I look at t equal to 0 plus, I have what? I have this. And then I'm going to reduce that to 1. So I'm going to reduce that to 1 resistor or inductor here. So that's what? That's 1. 1 plus 1 is 2. So I get a 2 Henry. I get a 6 ohm. I get a 6 ohm. I get a 6 ohm. And if we were talking about calculating this guy, right? If we were talking about calculating that guy, draw the nodes. Right? If I make this the ground, where's the ground? What's the voltage of our resistor? 12 volts. So if you said, well, 12 volts, I got to say, like, you're right. Right? So, I mean, I guess we could do this and calculate the current. And then say, the current, you know, when I go and I solve for this thing, it better give me 12 volts. But let's change the problem just a little bit. Let's say that we want to calculate this V6 right here. Okay? Because it's 12 volts. Right? We don't have to calculate anything. Okay. Remember, I've given some node in mesh questions and on final exams where it's just like this. And then you'll see people put like 2 pages down. And then there's one who just really just kind of looked at the circuit and said, oh, 2 volts. And I said, right on. Right? And that means that you're paying attention. But if you like doing node or mesh, I guess you're going to do mesh or node. So let's do this again. So the first thing that I got to do here is that I'm going to calculate IL of 0 minus. So if I calculate I of 0 minus, I'm assuming steady state. So that means that the switch is open. So in this case here, this implies that the switch is open. So when I look at this circuit here, at steady state, I really have this. And so if I'm following the current, we could see that this guy right here is giving me the I of 0 minus. But if I follow the current, let's just follow the current real quick. Current comes out of the power supply. Right, it comes here. It splits going there, and then it comes back up. And then, look what happens here. I see that this short is parallel to the 2 6 ohm resistors right here that are in series. So what does it do? It shorts them out. So these guys are gone. Right? Because we say that they're shorted out. So the short kills them off. So that means that the current of the inductor must be the current of the 6 ohm resistor. So therefore, the current of the 6 ohm resistor must be the current of the inductor, which then must be 12 over 6 gives me 2 amps. Okay. So now the switch is thrown. So now we're looking at 0 plus. And so when I put that 0 plus, I now don't have this open anymore. So my circuit then looks something like this. So I'm going to get 6, 6. Then I'm going to get my inductor here. That's 6 here. Like this. So now, what I'm going to do here is my job here is to then calculate the Norton parameters. So what I'm going to do now is I'm going to calculate Norton parameters. And what are my Norton parameters? I got to get I short circuit, I got to get Rn, and I got to get 1 over tau. Okay, so here we go. So what I'm going to do now is I'm going to remove the load, and then I calculate I short circuit across this point. So remove, load, calculate. I short circuit. So then my circuit looks something like this here. So that's I short circuit right there. So now I can't kill off these resistors now because I have this wire right here. But what I can do, actually, you know what I should have done? I should have left that inductor in here because I'm seeing a source. Because I should have redrawn this. I just realized this is a silly circuit because if I redraw this thing, aren't these two in parallel? So I get a 3 ohm resistor in parallel in series with that. So my circuit really looks like this. Right? Then I get this, a 3, a 6, and then I have my 2 Henry inductor. So this makes it a hell of a lot easier to calculate I short circuit. So this circuit really this can also look like this here. Right, so this is 3, this is 6. And we could see that I short circuit has to be the current of the 3 ohm resistor, but because it's in parallel with the 12 ohm resistor, we already know that this guy has to be 4 amps. So if I look at this guy, just this piece right here, we could see that I3 has to be the same as I short circuit, which has to be 12 divided by 3, which then gives me 4 amps. Right? I should have redrawn this instead of just jumping into the circuit here. So then, I'm going to keep it in this form here. So what do? I remove my load. I short that guy out. And you can see that I have to have 3 and 2. Is it in series or in parallel? Let's look at it. So now what I'm going to do here is that now I want to calculate Rn. So now I short this guy out. I got 3 here. I got this load. And then I have this guy 6 here. And this guy is going to be somewhere in here. I got to calculate Rn. So for starters here, if I look at these 2 nodes, my current's coming where? If I look at my current's coming here, then it has to split here. So if it splits, what happens to the 6 ohm resistor? Why is it a short? Because if I look at this node and that node, they got to be the same. So therefore, it's got to kill off this guy, and it should be a north resistance here equal to 3 ohms. So if I now have 3 ohms, so then that means then 1 over tau has to be what? Rn. Is this an inductor? Yes. Has to look like this. So then Rn is going to give me 3, and then I get 2. Thank you. So then I get 2. So that will be 2 hertz, 3 over 2 hertz. So then I have tau right here. So now I'm going to write up the solution. So if I write up the solution, what does it look like? if I write up the solution, I'm not going to have that the IL of t should be I short circuit plus IL 0 minus I short circuit e to the minus t over tau. So if I write this up, we saw that I short circuit was equal to 4. Okay, so it's 4 plus 2 minus 4 e to the minus 1.5 t. So if I look at this guy here, I'm going to get 4 minus 2 e to the minus 1.5 t amps, or I L of t. Now, does this make sense here? Well, we see that the inductor must be increasing in current here. Right? We're clearly seeing that it's going from 2 amps to 4 amps. So if I was to sort of like plot this guy, we're seeing this guy here. So he's coming in at 2 amps, and then it increases in current up to 4 amps. Well, why does it increase in current? Look at the circuit. Right? Why does it increase? Why does placing this short increase the current?
Well, it's the resistance to be half, or cut in half, once we use the short.
Once we use the short, what do you mean it's cut in half?
Or since they're in parallel, the resistance felt is 3 ohms instead of 6, so the current is able to be higher.
That's exactly right. So what I say here is that we were going to modify the circuit to calculate this guy. So when you look at this, if I know the current here, now this circuit, it looks really complicated, but the one thing that you got to remember here is that that current coming in here is being divided. I have the same 2 resistors, and they're going to the same ground node, so it cuts the current in half. So if I look for the voltage of this, I got to divide the current by half, and then I got to multiply by 6. So I'm really doing 6 divided by 2, so it's got to be 3. Right? So if I now go and I solve for this thing here, so to determine V6 ohm of t, what we're seeing here is that we have the 6 and the inductor coming in like this. So I see this guy, right? So I'm getting 6 here. So I'm seeing this inductor coming in like this, and then clearly I'm going to get half of this thing. So only half of the current of the inductor comes in here. So to calculate the voltage here, the voltage of the 6 ohm at this point then is then going to be 6 times 1/2 IL, which then says that I can multiply this by 3. So if I multiply this by 3, I'm going to get 12 minus 6 e to the minus 1.5 t volts. So very similar to this here, it's got to increase in voltage here. So if I go and I plot this guy, what am I seeing? Well, what was the voltage beforehand? Had to be 0, right? Why is it 0? Because we saw here that when this thing was open, that short killed off that voltage right there. So if I go and I plot this, what we're seeing here is that this guy's coming in, V6 at 0 minus was 0 volts. So then the switch is thrown and this guy jumps up to what? 6 volts. So then this thing jumps up all the way up to here and it goes to 6 volts. So from this line, you can see that this guy's going to increase by a value of 6 volts as it goes from 6 all the way up to 12 at t equal to infinity. So when I look at this guy, if I make this my 12 volt line here, we're seeing that this voltage here then jumps up like this. And this is the voltage of the 6 ohm as a function of time. Now, the question is, does this make sense? Right? Does this make physical sense? And the answer is absolutely yes. And that's because it's really nice and clean if you drew the circuit like this. And you can see when this guy dies off, this guy has to go to that 12 volts. They have to. Right? They have to go to that 12 volts. So, but wait a minute. I thought this was 6. Doesn't it divide the voltage by half? Let me say that again. Doesn't it divide the voltage by half? Right? Because look, that 3 is these two 6 ohm resistors. I'm after that voltage.
They're in parallel.
Yes, they're in parallel. Right? That guy's a little bit tricky. So what that circuit really looks like is it looks like this here. So when you redraw this thing, that 3 ohm is really like this with the inductor. And when that guy goes to a short, these two are still in parallel with the 12 volts, and I get 12 volts.